Today's online will be a bit of the material we'll cover. It's kind of a review of the previous week. Then we will go to discuss the stability for non-autonomous systems and some stability properties, which is like a UUB. Okay, we'll discuss later. We covered this in the previous week. So here is PSD function for non-autonomous systems. And W is like a label function, which is not only a function of x, but also a function of time x, time t here. The requirement for W to be a label function for non-autonomous system is 0 at 0 for all time. And W had to be greater or equal to 0, even it's not at the origin 0. Okay, the substrate 0. And in contrast, for PD, the only difference is here we replace, here 0 is the lower bound, right? But for the function to be PD, we replace the lower bound from 0 to positive definite function V here, okay? Then we call W is a PD function for non-autonomous systems. A function is called decreasing if it satisfies this condition. If for any time t, the magnitude of W is upper bounded by a PD function, then we call W is an decreasing function. An example is like this. For any time, no matter what time it is, the absolute value of W is always upper bounded by a PD function, which is this part, right? But for this example, you cannot find a PD function Vx, the upper bound this function, because this t squared increase to infinity as t go to infinity. So next is already unbounded functions. A function which is a W function that is a function of x and t goes to infinity as x go to infinity for any uniformly on t. Then we call it already unbounded for all time t, okay? So for this one, this e power minus t will decrease to 0. So that prevents W go to infinity. So the way you check out the already unbounded function is you can divide it into two steps, right? First, check out this. And for the first part, it's already unbounded if you don't consider t. And next, you consider this part. If it goes to 0, then it won't be an already unbounded function, right? Because for already unbounded, the whole function have to go to infinity. But this part, which is inside W, right, prevent the whole W goes to infinity. So you need to check two conditions, 1 and 2. If you just look at this part, the second part is if t goes to infinity, the value in the whole bracket will go to infinity? Yes, right? How about the first part? Not, because you have x1 here. x1 goes to infinity, which means the x norm will go to infinity, but it's bounded by 1. And this one, okay, the second part is okay, right? Which won't prevent you go to infinity. And this part is already unbounded for the autonomous case. And how about this one? Yeah, of course it's yes, right? Because the time part here is lower bounded by 1 over 12, upper bounded by 1. So here are some exercises we can do right now. The condition for PSD is more loose compared to PD. This function will go to 0 as t go to infinity. As t go to infinity, no matter what x1 and x2 is, right? Or what x1 or x2 are, right? Because the second part will go to 0 as t go to infinity. And that satisfies condition because for PSD, it says for PSD, based on the previous definition, for W to be PSD, it had to be lower bounded by 0 here. Lower bounded by 0 for any x, right? Even it's not at the origin. So it's PSD for sure. And how about PD? There's an equal sign here. And it's equal to 0 no matter what x1, x2 is as t go to infinity. You can check out this, divide it into two procedures. One is check this part. Another one is check the second part. And this part is PD for autonomous systems. The first part is PD for autonomous systems. And when you multiply this part can go to 0 for t go to infinity. So it's PSD, right? So it's PSD and it's not PD. And how about the radially unbounded function? Again, you check two parts separately. So this part is radially unbounded for autonomous systems, which means you don't consider any time elements. But for the second part, it goes to 0, so it prevents W goes to infinity, so it's not. And for decreasing, it means that the function goes to what? 0. It's upper bounded by some non-autonomous PD function, right? It's upper bounded by some non-autonomous PD function, okay? Non-autonomous because there's no time element here. So the way to check this is, again, divided into two parts. The first part is this, okay? And second part is this. And W omega W xt is it upper bounded by a PD function? Yes, right. It's upper bounded by this, okay, because of this part. The maximum value of this part is 1 and decay to 0 as t go to infinity. PD 就是 0 at 0, right? 0 at 0 and positive when it's non-zero. It's PD. PSD is, here we use minus 0 element. So if x is this, w is this, and it has to be 0 at 0. But equal to 0 for x not at 0. So it might be 0 somewhere other than the origin, right? It's PSD. Okay. PD only 0 at 0. And w upper bounded by a PD function. W can be upper bounded by this PD function. This is PD, right? So next, is it PSD? It's 0 at 0. Usually it's PSD, but for PD you have to check 0 at 0. And for non-zero, it could be 0. Wxt equal to 0 at x1, x2 equal to 0. So is it PD? Can you find W equal to 0 at somewhere belong to R2 minus 0? Somewhere other than the origin. Can you find those x such that W is 0? Do you? No, right? So it's PD. Is it radially unbounded? Yes or no? Divided into two parts, right? First part is this, second part is this. Is this part radially unbounded? Radially unbounded means W or V that for non-autonomous case goes to infinity if x norm goes to infinity. So check out the first part. Is this autonomous function radially unbounded? 你可以找到任何的 x norm 大无穷大 v 会大无穷大吗？不会嘛。Counter example will be x1 go to infinity, x2 is 0, which implies x norm goes to infinity. But what is v? Vx at this time is 1. So x norm goes to infinity, but v doesn't go to infinity, so it's not. If the second term is exponential minus t, then this term goes to 0, right? As t go to infinity, then it's not really unbounded. Because we say the whole e or w had to go to infinity. And in this w function, it's not only a function of x1, x2, but also a function of t. So we need to check x and t. That's why we divide it into two parts, the first part and second part. If it's PD, then it must be PSD. If w is PD, but not vice versa, okay? If it's PD, it must be PSD, right? PD says it's 0 at 0. And PSD is the condition is more loose. Here is 0 at 0, so it's equal to 0. X is 0. Let me ask you a question. If w is greater than 0, w greater or equal to 0? Yes, right? 比如说1大于0嘛，那1有大于等于0嘛，懂吗？ So if it's PD, it must be PSD, right? So if it's PD, it must be PSD. 如果说它等于，那就错了。So to check RU, you can divide this function into two parts. First, you need to check if this function is radially unbounded. Is this function radially unbounded? Yes or no? Radially unbounded for autonomous systems. For autonomous systems, we use Vx, which goes to infinity if x norm goes to infinity. So is it if it is radially unbounded? No. Why? So the counter example is x1 goes to infinity, but x2 is 0. Then this function goes to 1, right? Which doesn't go to infinity. There are 3 more examples. So example 3. So PSD, is this function PD? So first check out this. Is this PD? Yes, right? Will this be 0? So what's the upper and lower bound of this? It's lower bounded by 1 and upper bounded by infinity. Which 1 goes to 0, right? 它不会到 0. 所以你就 guarantee 说 okay, the whole function will only be 0 when? Because the time, the upper and lower bound of t doesn't go to 0. So the w function won't be 0, right? Because the w is the product of the first part and second part. So the first 2 cases will be fine, okay? Now, is it radially unbounded? First, check out this part. It's yes, right? It's RU. We haven't considered the time component. So the second part, will this part prevent the whole product goes to infinity? Yes or no? So it's lower and upper bounded by 1 and infinity. The product of these two, 1 goes to 0. So w can go to infinity. X non go to infinity, 对不对? Right? So it's yes. So the last example, decreasing, I guess you again forgot the definition, right? So for decreasing, it's upper bounded by some PD autonomous function. So again, first check out this part. It's PD, okay, that's good. And is this one upper bounded by some constant or not? This w is already a function PD that times some t squared plus 1, right? So can you find another PD function that upper bound this PD function times the t squared plus 1? Can you? No, because t squared goes to infinity. You cannot find another PD. Example 1, 2, 3, none of those can satisfy the 4 options, right? So none of those will be satisfy the 4 conditions. But example 4 is satisfy all the conditions. Why? Because this part is lower and upper bounded by constants, right? It's lower bounded by 1 over 12 and upper bounded by 1 as t go to infinity, right? So if this part is PD, w will be PD, and of course have to be PSD. How about radially unbounded? Because this part is lower and upper bounded by constant, you only need to check the first part. So it will be radially unbounded. And again, this one. What's the lower and upper bound of this? It's lower bounded by 1, upper bounded by 2. So again, it satisfies all the 4 conditions. I list 5 scenarios, 5 conditions. And these conditions are used to check the properties of the system. So if you can, given a nonlinear system, if you can find, say, given a non-autonomous systems, to prove the stability of the system, the next thing you will do is to find a variable function, Tx. So if this V satisfy the first and third condition, this one and this one, you can find a V that's PD and V dot is an SD. So the relation between this V dot and this is you use the directional gradient, right? V dot equal to what? Okay. If you can find a V that is PD and this V dot, which is obtained by substituting this dynamics, and that V dot is an SD, then we say this non-autonomous system is stable. In the previous case, we discussed non-autonomous system, right? for autonomous systems, x1, x2, we find some virtual function that's called the above function. Okay, we say if v is PD, which it is because only 0 at 0, and we find v dot is lower and upper bounded by 0. For example, v dot is, for the pendulum case, right, we have what? Some x2 squared, right, which is an SD. Okay. That means that v dot equal to 0 when x2 is 0. Okay, so it stops at here. V is a constant. It's a constant. It's a constant because v dot is 0, right? It's constant. Right. So what's the invariant set in this case? Invariant set is the projection of this v onto the state space or the phase portrait, right? 对不对? Okay. But this is for autonomous case, which you have these two conditions. Now, for non-autonomous case, you have time element in your above function. V dot will be a bit different, which when you take the partial, you have the time element here. So if you substitute your dynamics into your V dots and find that is PSD, okay? Then you know that system is stable because the solution of the x never go outside of this invariant set, right? And that's the definition for stable. And it's called uniformly stable, more restrict, right? Uniformly stable. If it satisfies 1, 2, 3, so only difference is the second condition. V is decreasing uniformly. 那这个是 global for the US, uniformly stable. 这个是 globally uniformly asymptotic. The second case is satisfy the first, second, and third conditions. Then we say the system will be uniformly stable. If it satisfies the first 4 conditions, 1, 2, 3, 4, the system is globally uniformly stable. Okay. For 1, 2, 4, 5, uniformly asymptotically stable. Okay. So takeaway is if this one means uniformly. Uniformly means it doesn't depend on time. The convergence doesn't depend on time. And if this one is satisfied, it's globally. It doesn't depend on the initial condition. For asymptotically stable, it had to be satisfied the fifth condition. And these two, you can choose one of these two, okay? If 3, then it's stable. For 5, it's asymptotically stable. It's even better. So the previous few slides that we define the decreasing, radially unbounded, PD, PSD, those are the tools to define the stability for non-autonomous systems. So now there are a few functions to be defined, and we call it class K or K infinity functions. So what is class K? A function alpha that maps from this space to this space. So it's mapped from a scalar to another scalar. Is said to be a class K function if it's strictly increasing and 0 at 0. 0 at 0 and strictly increasing. The second condition is built on top of the first one. It means that infinity function, if this A is equal to infinity, means it's defined, this alpha function is defined from 0 to infinity. And the alpha function goes to infinity as the R go to infinity. 如果之后有人跟你讨论一直讲说，这种方程要叫什么？就是这种符合他说的， is 0 at 0 and increasing， 这样这一种或是这一种，这种function要叫什么？你跟他说 class K， 他会吓到，对吧？因为 class K 就是包含所有的这种function， 这样不是比较有深度一点吗？对吧 ？So a class K function means it's 0 at 0, 0 at 0, and it's strictly increasing. Means it had to be increased no matter where it is. Okay. Is this function strictly increased? So the slope here is 0. V prime here is V prime at xp. V prime at xp is 0. Then it's not a class K function. Okay. Because it's not increased here. 懂吗 ？Strictly means 一定要 increase， 你不能停下来。Okay, strictly means you have to always increase. You cannot be, be constant at somewhere. Okay. So the second one is built on top of the first one, right? So it had, and the additional condition is A. It have to be goes to infinity. Define all the way on this axis. Okay, so you have to always increase no matter where you are. So it's hard to imagine, so I give you some example. 10h. What's 10h function looks like? 10h function is 10h function is upper bounded by what? It's something like this. Okay. It's upper bounded by some constant. 1 or 2 pi, I forgot. Okay, it's upper and lower bounded by 1. So it's between -1 and 1. Strictly increase. So the way to check is you take the partial of this function on its argument r, and you obtain sec h square, which is always positive. Then it must be strictly increased. But it's not class K infinity. Why? Because it's bounded by 1. It doesn't go to infinity. Remember in the previous slide, we say the function had to be go to infinity. So the second example is class K and K infinity because it's strictly increased and it's go to infinity, it's R go to infinity. Then next, what is class KL function? Continuous function beta, it had two arguments, mass from 0a and 0 infinity to 0 infinity. Yeah, two arguments, R and S as argument. And beta is a scalar, so it's a scalar function. So it belongs to a class KL function if you fix S and increase R, and the whole function is class K. And the second condition is if you fix R and increase S, the whole function is decreasing with respect to S. Then we say class KL function. This one says we fix S. Yeah, two arguments, right? So we fix this one. And the whole function belongs to class K with respect to R if it's increasing. If we fix this and it's class K, it belongs to class K with respect to R. And we fix another argument R and increase S. And the whole function is decreasing with respect to S and goes to 0 as S goes to infinity. Then we say the function satisfying these two conditions will be class KL. So you can consider this S as time, okay? This R as your states. So the first one is you fix S and you take the partial with respect to R. And you find that it's always positive, which means beta with respect to R. And the second condition is you fix R and find the partial with respect to X and find it's decreasing. Then it belongs to class KL function. Again, you can check this function follow the same procedure and you find is also class KL function. What's class KL function help you in the system analysis? Okay, so first, there's two lemmas. The first lemma is that V is said to be already unbounded if both alpha 1 and alpha 2 are K infinity functions. Means it's strictly increasing and go to infinity as x go to infinity. Okay. Now the lemma 4.5 says an nonlinear non-autonomous systems is said to be uniformly asymptotically stable if there exists a KL function beta. Okay. That upper bounds these states, norm of the states. Then we say it's uniformly asymptotically stable because it converges to 0, right? 这个方程会随之间 converge to 0， 对不对？ So the x here is only a function of time. It's a function of time. And when you increase time, the whole function will decrease. You fix x. You fix the first argument, which is the initial condition, and you increase time, right? Beta will go to 0. So as time increases, this x norm will go to 0. But the first argument is for the initial condition. No matter where you are, this function guaranteed to be will go to 0. Okay, and it's the upper bound of this. So upper bound goes to 0, x norm has to be go to 0. But it's useless. Why? We don't know the solution of x. We only know the dynamics. We don't know the solution. So that's why we don't know the solution, and usually the alternatives will be checking out the behavior of the able functions, not the solutions. Okay, so that will be the next topic, kind of slightly similar to this. So that's for today.